because my usual stunt is to forget that. Okay, so we're gonna start off everything shortly by playing a type of game. It'll be a fun game. Today's topic is formally hypothesis testing. So Thursday's laboratory, we kind of set you up for that. And hypothesis testing is the advanced way of the old Sesame Street game where they show you pictures of 5 or 6 things and then they sing a song, and they sing better than I'm going to, but here goes. One of these things is not like the other. One of these things just doesn't belong. Can you guess which thing is not like the other? I think you're supposed to guess it before I finish my song. Okay, so that's the game we're going to play. So first, let me switch cameras. And I'm kind of doing this experimentally because I want to be sure. Jordan wants me to continue singing. Jordan, dude, you have peculiar tastes if you think that my singing is that. So you should see all of this, which is what I'm after. I'm going to put some items on the table, and then we're going to sing our song, so to speak. And I'm going to pose a question once I get them all laid out. See if this one will fit in there. And I had one more set up. That's going to have to do. Okay, so these items are all electronic looking widgetronics things. But of the 5 items on the table, how many of them are data storage devices? So I know you can't see, the red thing is an integrated circuit. It's an MCP 3008 chip. So you can
there's 2, I guess there's a solid state drive and then there's a micro SD.
And there is a ordinary hard disk drive.
I didn't see that. Oh, I have a passport.
This is a microprocessor. It's got wires and shit. That's not a data storage device. This is a Raspberry Pi Zero with no components in it, so that's not a data storage device. Now we have 3 data storage devices. Which one of the 3 stores the most data?
Probably your passport.
Correct, 4 terabytes. Of the 2 that are remaining, which one stores the most data?
Your solid state drive.
Actually, they are identical. That is a 500 gigabyte SD, micro SD.
Oh, I couldn't even read that.
So you all did good in that game. You were able to tell that some things belonged with the other, but when we started out, as far as a distribution of thinginess, everything was a modern electronic device. So let's play the game again, but we're going to switch to something different. Hopefully these will fit. So here is a banknote. Here's another one. Here's another one. And there's another one. They're all the same thing, right? Because they're all green?
No, they're worth different prices.
Okay, so your conjecture is that they have different values. Well, because that one's got a 5 on it. That's got a 1000 on it. This one doesn't even have numbers on it because in England, if you have to use numbers, you're wrong. And this one doesn't even have numerals on it that most of us can recognize.
5.
And there's a 5 right there. Look, those both have a 5 on it, so they got to be the same, right?
No.
Okay, so again, it's very natural, same versus different. In that case, you are rejecting my assertion that these are the same things. And you're basing that rejection correctly on what?
that, yeah, they might be all green, they might be currency, but they're worth different types.
So there is some difference in it that's big enough for you to reject the assertion that they are functionally the same thing. Okay, good. We will play that game. We're going to do more with currency because that's what I have the most bunch of useless currency when you're not in the country that they apply to. Okay, so here's blue, and here's another blue. Same or different?
Different.
Different.
One looks like it's from Chile and the other one's from Europe.
Okay, so again, the differences are large enough. In this case, the descriptive statistic you chose was the nation of origin. I guess not region. So that's almost like a mean value. So the mean of the upper one was Chilean, and the mean of the lower one was EU. The other difference you could have picked is one had a 10,000 on it, and the other one has a 20 on it, and those are vastly different numerals. Although they're actually converted to a common currency. They actually at one time, they were pretty close in functional value. Okay, so now we're gonna have some real fun. There's a blue one and an orange one. They both have Spanish looking words on them. They both say viente value, so that's 20. This has a 20, viente. It's got a picture of some old sun worn out person on it. Same or different?
Different.
Probably the same.
I
They
don't
look
know much
about
about
20 pesos.
That was a trick question. I mean, obviously one's orange and one's kind of bluish. If we go with your prior descriptive statistic of the nation of application, the upper one is Mexican pesos. The lower one is Bolivian. I think they're called pesos or bolivianos. So Mexico, Bolivia, both south of the United States, but other than that, not a whole lot in common. They both speak Spanish. And while we're doing the whole Spanish speaking thing, here's another one with a 5 on it. And this has a 5 on it. Same or different?
Different.
same.
Correct. And what metric did you choose to make them different?
By the way, that is a very beautiful bill.
It is indeed.
Yeah. The prettiness of the bill and the origin of the country.
Okay, so again, we're using a metric, in this case, nation of origin, kind of like a mean value or a variance. And then prettiness, I think, would actually come under variance. For what it's worth, the lower one is 5 colones, which is the currency in Costa Rica, and they don't actually use these bills anymore. So if you get this bill is pristine. You buy these from vendors on the street for about 10 colones, so they're making a 2-to-1 on the last runs of these. So it's real money, but nobody uses them because they're too beautiful. They've gone to relatively ugly money like the rest of the planet. Last one. Oh, this will be fairly easy. Same or different?
Different.
Yeah, one's got 1,000 on it, one's got a 10. So you would argue that their measure of central tendency in terms of just numerical value is different. One's red and one's kind of bluish. That's different. The upper one is from Costa Rica. The lower one is got German looking words on it. And for what it's worth, the lower one is no longer in use. That's a 10 Deutschmark note, and they abandoned Deutschmarks roughly 30 years ago, and they use the euro now. I'm told if I take this to Germany with me next time, I can either trade it straight across for a 10 euro note, which would be patently stupid, or I can sell it to a collector for somewhere in the ballpark of 80 to 100 euros. So I'll take that second case if I'm going to sell it, because I have no particular sentimental attachment to that. Okay, so that was intended to introduce hypothesis testing, because the main goal of hypothesis testing is to answer a variation of the question, is it the same or is it different? Oh, don't click on that. I almost ended the call, which you all would have been happy with. So let me get on to the actual class. Calendar goes away. Recording is running. And this is our current lesson. So let me push everything off here to the side. And lesson 15, hypothesis testing. It's a procedure to help us systematically decide if two data collections are similar or somehow substantially different. So you've all done that very successfully with money. You did it very successfully with computer components. And now if I were to ask you, is the collection of red umbrellas and black umbrellas different? And you'd probably say, yes, one's red, the rest are black. Also, the total quantity is different. So that's where we're headed to. Our objectives today are to apply fundamental concepts involved in probability estimation modeling and descriptive statistics. That's really what's going on. And we're going to briefly discuss the concept of a hypothesis and then the important components, the null hypothesis, the alternative. The normal distribution model is commonly used. It's one of many. And whether we have an animal that has just one tail, or we have the always preferred two-tail animal, a famous push me pull you. Actually, they don't have tails, they have two heads. Twice the fun and none of the mess. And then the attained significance, and we will close out with decision error and an example. I want to go back to our laboratory from last week, lab 13. Hopefully this is it. And somewhere down at the bottom of lab 13, we had, there we go. And we beat on you repeatedly. Is set 1s and set 1 the same or different? One's green and one's blue. But that would be like if I had multiple instances of one type of currency. They're perhaps individuals, but they're very similar. And then is set 2 and 2s the same or different? We would probably conclude that they're the same just by looking at it. But the one of these things belongs with the doesn't belong is the set 1 categories and the set 2 categories the same or different? And that was not rhetorical. I want an answer. So somebody answer that.
They look pretty different.
They look pretty different. Okay, in this case, these happen to be, the picture is a histogram, so it's counts within bins, and clearly the set 2 category bins are several hundred, whatever the horizontal units is, away from the set 1. Probably no hypothesis testing required. If we were to speculate what the next value from a set 2 sample would be, what's a good guess of the most likely next value from set 2, just by looking at it?
500.
Yeah, somewhere around 500. I agree. What's a good guess of a set 1 next value?
Like 50.
50-ish. What's the probability of the next value having a value of 200 according to these pictures.
Effectively 0.
Yeah, we don't expect to see that. So if we recover a 200, we would tend to think we'd made some kind of mistake, or we had sampled from a fourth as yet unknown set. Excellent, very good. The computational thinking concepts that are mainly in effect with regards to hypothesis testing are our friend abstraction, and what we just played with money and computer component widgets and set ones and set twos are pattern recognition. So we're going to codify that in some sense to leverage that pattern recognition in some systematic fashion. In statistics, when we want to start asking questions about the data and interpreting results, we should get onto our motorcycle and drive away as fast as possible, or use statistical methods that can provide us with a confidence or likelihood about the answers. And in this context, confidence or likelihood is not necessarily the same confidence or likelihood that we deal with in day-to-day life. They are descriptive terms for a particular estimated value of something. So when we say confidence is high in a statistical sense, that means something very precise. I'm pretty confident I'm not going to wreck my car driving to school today is a different use of that particular English word. They're related, but they're not the same. In general, the entire class of methods is called hypothesis testing, or statistical hypothesis testing, or significance tests. The material for today's lesson, and lab for that matter, is are listed here, plus our formal textbook, which I actually don't have cross-linked. That's an error. So these are all available at a couple of websites, towardsdatascience.com, one that you should start becoming familiar with for the remainder of the course, because we're going to use the heck out of it. Another one is machinelearningmastery.com. And these three titles, hypothesis testing and machine learning, demystifying hypothesis testing with simple examples, and a general introduction to statistical hypothesis testing. You're going to want to read too, because they do the demystifying, and what I'm going to do is mystify hypothesis testing. So if it makes sense right now, I should be able to destroy that in the next few minutes. So first we'll start with some fundamental concepts. What is hypothesis testing? Hypothesis testing is a statistical method that is used in guiding statistical decisions, usually about the population, based on experimental data or based on samples that we have obtained from the population. It's essentially testing an assumption that we make about the population parameter. As an example, you might state that on average, students in the class are taller than 5 feet 4 inches. Or you might say something like, an average boy is taller than an average girl. As long as you stay off that island where Wonder Woman came from, maybe that's true. Or a specific treatment is effective in treating COVID-19 patients. So those are all assertions. The last one is probably more timely in the TV news. But while we can say that, I'm a doctor, so I can certainly say this treatment is effective in treating COVID-19 patients. The natural question from you would be, how can you back that assertion up? At that point, since it's obvious that I'm lying, I have to back it up using statistics, because statistics is the important tool of liars everywhere, and truth tellers too. So we need some mathematical way to support whatever assertion we're making that it's true. And we do that by validating these hypotheses, or assertions, if you will, and basing our conclusion on random samples and empirical distributions. So to back up the first assertion, students in class are taller than 5 feet 4 inches. Well, a class is 50 to 100 people. It's quite feasible to measure the height of the entire population. So that assertion is actually very easy to determine. You would measure everybody in the class, you would compute the average, and if the average height is 5 feet 4.1 inches or greater, if that average value is greater, you have backed up that assertion. Not a very strong backup, especially if the average comes out to be 5 feet 5 inches, because if you're going to extrapolate that assertion to more and more classes, you don't have a whole lot of evidence to back it up. Average boy taller than average girl, that's a little harder. There's roughly 8 billion people on the planet, and I think the planetary age cohort is something like in the 18 to 20-year-old range. That's where most of the population of the planet exists right now. So if you declare anyone under 20 in the boy-girl category, you probably have 2.5, 3 billion of them, maybe more. Let's go with 3 billion. It's pretty infeasible to measure every single one of them. That's an awful lot of tape measures you have to make and then ship by Amazon to your official measuring person, and they have to log it back into their Facebook page to get the measures. So instead, what we would do is randomly identify 10 or 20,000 boys and girls, and then have them come in for a $100 Amazon gift card for participating and measure their height. And then we would then take all the boy height measurements, compute their average, same for the girls, and then test the assertion, is the numerical average of the boy heights bigger than the numerical average of the girl heights? If that's true, you have evidence of that assertion. As for the COVID-19 treatment, you give them the treatment and then you see how many of them are dead as soon as the needle comes out of the arm. And if you keep that time frame short enough, the treatment looks great. Look, it didn't kill them, must be good. That's the basis of hypothesis testing. Now, those 3 examples I just stumbled through talking are good examples, but they're not very good hypothesis tests because I didn't put much rigor into it. I just measured as many as I could and looked at a number, and it's quite possible that I can pick randomly 10,000 boys that are relatively short for boys and 10,000 girls that are relatively tall for girls. And at the end of my measurement, I will assert something that is in fact not true. So we use hypothesis testing as a way to guide experimentation. And a hypothesis test evaluates 2 mutually exclusive statements about a population to help us determine which statement is supported by the sample data. If our particular assertion is indeed supported, we might say that we have found a result that is statistically significant. And here it's bold-faced because the words statistically significant have a very particular meaning. It means that the difference or the statement you're asserting has been tested with a hypothesis test, and it's found that the attained significance, which is a calculation, is bigger than some sentinel value. Therefore, statistically significant. So we start with a problem. We make a hypothesis. And in this case, a hypothesis is not quite the same hypothesis as in the scientific method. We make a statement H sub 0 called the null hypothesis, and we make a statement H sub 1 called the alternative hypothesis. And an example of a null hypothesis is the average height of the difference in average height of boys and girls is 0. The alternative is the difference between average height of boys and girls is greater than 0. Boys are taller. That's what's meant by a null and an alternative and mutually exclusive. So 0, greater than 0, or we can actually get more fancy with it, but that gets us started. So the important elements of hypothesis testing are stating the null and the alternative hypothesis. Ultimately, we're going to apply a statistical test, and that test is going to be on the null hypothesis. And the usual symbology is H sub 0. It's often called the default assumption, or the assumption that there is no difference, nothing's changed. In inferential statistics, the null hypothesis is a general statement or default position that there is no relationship between two measured phenomena, or no association among groups. In other words, it is a basic assumption made based on domain or problem knowledge. Example, a company's production is 50 units per day. Might be a null hypothesis. An alternative hypothesis, often called the first hypothesis, or H sub 1 for short, is the some other hypothesis. And all we know is that from evidence that we can make samples, and all we can determine is whether H0 can be rejected or not. The alternative hypothesis is used in testing, and it's intentionally contrary to the null hypothesis. It's usually taken to be that the observations are the result of some real effect with some amount of chance of variation superimposed. For example, the null hypothesis for a prior example, a company's production is 50 units per day. A perfectly legitimate alternative hypothesis is a company's production is not 50 units per day. So we go and measure the production, and one day it's 50, next day it's 49, another day it's 51, then another day it's 20. Either the null is supported or not. And then the basis of the test is often based on normalization or standardization. And all the hypothesis testing we discuss are going to revolve, at least for the near future, around these terms. So this first image, there are 1, 2, 3, 4 normal, those are dense, normal density curves. So we have the blue one, and the blue one is kind of steep and pointy. We have a green one, and if I were to ask you, if I were to give you an observation of, say, -2.5, is it more likely it came from the blue distribution or the green distribution according to that plot?
Green.
Green.
Good. If I were to say another one, if we observed a 0.0001, more likely from blue or green?
Blue.
More likely from blue. Okay, so it looks like you guys got hypothesis testing wired. Now we'll complicate it with arithmetic. 0.0001, more likely from blue or red?
The same. Or actually, no, probably blue.
Blue.
I don't see how you can actually tell the two apart, because that value is really close to 0, and both of them are centered at 0. So I tricked you legitimately. If I made 10,000 observations of 0.001, and that's all that kept coming up, then more likely blue than red, because the variance, or how wide the blue distribution is smaller. So in the first image, we saw different normal curves. They have different means and variances. So the blue curve, the red curve, and the gold curve all have a mean value of 0. But the variance of the blue curve is quite small, 0.2. The variance of the red curve is larger, value of 1. The variance of the gold curve is 5 times larger than the red curve. So there's quite a bit more variability in the gold population than the blue population. Similarly, the green curve has a variance of 0.5, so it's wider than the blue curve, but more importantly, its measure of central tendency is -2. So it appears shifted left relative to the other 3 curves. And if the distance between 2 particular curves is far enough, we get back to our set 1 and set 2 pictures. And when they're far enough apart, we can easily tell by visual inspection that things are coming from different distribution. And what hypothesis testing is aimed at is how to handle the cases when the curves aren't necessarily obviously far enough apart. So the second image, we see a standard normal distribution broken up center to mean of 0, and each of these categories is showing 1 standard deviation away from the mean. So if we knew the population standard deviation and we observed normalized values between -1 and 1, that would explain roughly 68% of all the anticipated observations, no matter how many we made. If we go between -2 and 2 standard deviations, we can explain 95%, plus or minus 3 standard deviations, 99%. So that's the whole 6 sigma thing that was used in Japan to make awesome Toyotas. So let's suppose this indeed is our population distribution. If we were to take a sample, normalize it so we think it comes from this distribution, and the example we observe is 4 standard deviations away from the mean. Is that a common occurrence?
Could you say it one more time?
We take a sample, we normalize it, and it turns out that it's 4 standard deviations from the mean. It comes here at 4.
Yeah,
So-
no, our model's probably wrong then.
So you would conclude, and I agree, that that observation is unlikely to have come from this population. Alternatively, if we get a value of 0, we have good evidence that it came from that population. That's
Excuse me, Professor. Excuse me.
yes.
Okay, could you re-explain that part, please? Because I don't really understand what your question was. I'm sorry.
Okay, so I said that let's pretend we have a population that looks like this normalized curve.
Mhm.
And I go ahead and take a sample, normalize it, basically subtract off the mean and then divide by the standard deviation. And when I get done, my normalized value comes out to 4.
Mhm.
So if that is indeed the underlying population distribution, it's not impossible, but it's quite unlikely that I would expect to pull a 4 out of just any old sample. So I would conclude that it's likely that that particular observation did not come from this distribution. I have no guarantee, but it's pretty unlikely it came from that distribution. It's more likely it came from a distribution that's shifted to the right relative to this one.
Okay, thank you.
So a variable is said to be normally distributed or have a normal distribution if its distribution is the shape of a normal curve. I wish I could do a Homer Doe on that. which is a special bell-shaped curve. We're all pretty familiar with this by now because we've hit you in the head with a bell a few days in a row. The graph of a normal distribution is called the normal curve. And in the case of a normal distribution, the mean, the median, and the mode are equal. And then I was using standardized normal distribution. So by definition, this is a convention, a definition. A standardized normal distribution is a normal distribution that has mean of 0 and standard deviation of 1. So our second picture. There's a metric that we can compute of an observation called a z-score. And it's a method of expressing an observation relative to some group mean value and some group standard deviation. To obtain a z-score of a particular observation, we calculate its deviation from the mean and divide it by the standard. We calculate its distance from the mean and divide that by the standard deviation. So in this particular formula right here, for the time being, this x bar, think of it as the population mean value. And S is the population standard deviation. And then we make an observation that we think might be from that population. Our observation is cap x. We subtract off the population mean. We take that result, we divide it by the population standard deviation. And what we have left is the z-score. And what the z-score is doing is telling us where on this axis that observation will lie, assuming the underlying distribution is this standard normal distribution. So that's called normalization. So it's one way of standardizing a score, and so it can be referred to with a standard normal distribution curve because we can go look those curves up in tables in the back of our statistics book, which we haven't had the statistics class yet, but someday you will. Assuming they still use books by the time you take it, there'll be tables in the back of the book. You can learn more about these at the statistics how-to on z-scores and simple psychology. So a z-score is just a rescaling of data. It's rescaling it so that if it falls on the -infinity to infinity axis, and if it happens to coincide with the population mean, it will be right here at 0, and it is scaled to the population standard deviation. When we build our hypothesis tests, depending on the question we're asking, we can have a test that has one tail, like ordinary animals, or two tails. And the one-tailed alternative is actually easier to wrap your mind around in the first case. It's either less than or equal to some value or greater than. And so the one-tailed test divides our hypothesis region into a set point and then a region that is rejected. A two-tailed test extends that idea, and it says that is our anticipated hypothesis value between some lower and upper bound, and we can reject on being too small or reject on being too large. You can read more about these tailing in this Wikipedia, and again, simplepsychology.org. The next term we're going to introduce is called level of significance. This refers to the degree of significance that we, ahead of time, decide to accept or reject our null hypothesis. 100% accuracy is not feasible for accepting or rejecting a hypothesis, namely because there's not enough money in the world and won't be for the next 5 or 6 million years to be able to afford 100% accuracy. So all we can do is get close. So we have to select a level of significance. It's normally denoted with a letter of the alphabet called alpha, and unless there's other circumstances, the default is usually 5%. And what that level of significance is actually really doing is we are establishing an acceptable amount of error that we'll look at shortly. So if the level of significance is 5%, there's a related concept called the confidence, which would be 95%. The smaller alpha value suggests a more rigorous interpretation of the null hypothesis, such as 1%. But consequently, even though the confidence is increased, our range of values changes dramatically. We'll see that later in examples. The p-value, or calculated probability, or attained significance, so those three terms all usually mean the same thing, is the probability of observing the data that you've collected, assuming that the null hypothesis was true. Let me say that again. The p-value is the probability or the chance of observing the data you have collected if indeed the null hypothesis was true. And we already know backdoor ways to do that. We could simply use our simulation tools and just simulate 50 or 100,000 observations from our population, because we can go into God mode at that point, and then determine what the probability of a particular sample sequence that can be obtained. In fact, that's actually how these are all built originally. The p-value represents the strength of evidence against a null hypothesis. Accordingly, we will encounter two situations. We have strong evidence to reject the whole null hypothesis, or we do not have strong evidence to reject the null hypothesis. Let me take you on a thought lesson back to our set 1 and set 2 pictures. Remember, set 1 was the blue and green, all kind of centered at 50, range between 0 and 100. And set 2 was the orange and gold, and it ranged from 400 to 600, I think. Oh, actually, I got it right here on the Pictionary. So again, just looking at it, is there evidence that the blue and the green have a mean value that's 10 times smaller than the mean value of the gold and the red? Yes or no question?
Yeah.
Yeah, there's pretty darn strong evidence that blue and green are quite a bit to the left of red and golden.
In this case, what's the evidence?
The evidence is the distance between the two sets.
Okay.
If the sets are not far apart, the evidence is weaker.
Okay.
So the p-value is often compared to a pre-chosen alpha value. And when that's the case, a result is considered statistically significant when the p-value is less than the alpha value. So if your p-value is less than the chosen significance level, then you reject the null hypothesis, i.e. you are accepting that your sample has given reasonable evidence to support the alternative hypothesis. Again, if in the case here, the distance between green and blue is pretty large, the green and blue distance to the red and gold distance is fairly large. So that's strong evidence that those are not the same collections of data. They didn't come from the same underlying distribution. If the p-value is bigger than alpha, we usually choose do not reject. If the p-value is less than alpha, then we reject. When it's bigger than alpha, the do not reject is any differences we observe are not significant. If p-value is less than alpha and we reject the hypothesis, any differences we observe are significant. And the blue curve here is assuming the null hypothesis is true, and the p-value is evaluating the area on the right and the left of the curve where it's unlikely to have obtained observations from this distribution. Not impossible, but unlikely. So let's suppose we took 3 samples from this distribution, and the first one was right here. That's a pretty likely observation. The second one was here, and the third one was here. So we have 3 right here in the middle. It's quite obvious from this drawing that those are very likely to be observed, and so we would state that the null hypothesis that they're from this distribution is supported. But if we got one observation here, a second one here, and one out here, that's not impossible, but that's quite a bit less likely than to get 3 somewhere in the middle. If we got 1 here and 2 in this unlikely region, that's even more unlikely. And if we got all 3 completely outside the likely region, we'd be very uncomfortable saying that those samples came from this distribution. So if we're performing a test of whether our data sample is normal or not, and we calculate a p-value of 0.7, we would state something like, the test found that the sample was normal, failing to reject the null hypothesis at the 5% significance level. The complement of significance level is determined by subtracting it from 1 to give a confidence level, and the hypothesis of the hypothesis given the observed data. So similarly, if we compute the confidence, the test found the data was normal, failing to reject at 95% confidence. So as a simple thought experiment, let's suppose you have a coin and you don't know if it's fair or tricky. So let's a priori establish a null alternative hypothesis. It's a fair coin is our null hypothesis, and our alternative hypothesis is it's a tricky coin at alpha equal to 5%. Now these are real coins, these are not Bitcoins, you actually have to flip it. So now let's flip the coin. If it's a fair coin and we only get to make 1 experiment, we really can't learn very much. A fair coin, we should get heads half the time and tails half the time if we do a lot of flips. So getting 3 heads in a row and then a tail in 4 flips on a fair coin happens more than we can imagine. So we toss the coin the first time. Let's say we get a tail. And our best guess at p-value at that point is 50%. We toss it a second time and get a tail. The p-value is 50 divided by 2. It's now 25%. Let's suppose we toss it 6 times in a row and we get 6 tails. Our p-value is 1.5%, but we set our significance level at 95%, or we will accept a 5% error rate, and we find out that we are beyond our acceptable error rate. Thus, our null hypothesis is not supported. We would reject the null hypothesis and propose that the coin is not fair. So if you flipped a coin 6 times in a row and you got tails all 6 times, we would intuitively conclude that there's something funny about the coin. And statistically, we can support that intuition that there's something funny about it in that the level of attained significance, the chance that the coin is fair, is pretty small. So we would reject our null hypothesis that the coin is fair and propose that the coin is not fair. There's more explanations available at these 3 references, and here's some YouTube videos that will confuse this even further. And our next concept is reject versus failure to reject. The p-value, or the attained significance, is a probabilistic estimate. It's a result of a computation, actually. And that means that when we interpret the result of our tests, we don't actually know what's true or false, only what is likely. Rejecting the null hypothesis means there is sufficient statistical evidence from our samples that the null hypothesis does not look likely for the particular population. If that's not the case, it means there's not sufficient statistical evidence to reject. So we can think of the statistical test as the dichotomy of rejecting and accepting. The danger in practice is if we use the word accept. Our English language suggests that if we use accept, we would conclude that the null hypothesis is in fact true, when in fact we don't actually know. Instead, it's considered safer to say, do not reject or fail to reject, as in there is insufficient evidence to reject it. That's a subtle point, but it's important later on in this class, as well as in your other classes, where you are examining experimental results. Remember our lecture on causality. Very few things we encounter in our statistical engineering world that are data-based can we really assign causality to. At best, we're getting very strong correlations. And so keep that in mind as you proceed through this. The interpretation itself is probabilistic. It means that the evidence of the test may support an outcome, but in fact be wrong. For example, if the prescribed alpha value is 5%, it suggests that about 1 time in 20, the null hypothesis would be rejected by mistake, or be failed to be rejected by mistake. And lots of things can be attributed to that. Noise in the sample itself, getting a few values here out in the unlikely range, which indeed came from the distribution, they're just unlikelies, would tend to give us cases where the null hypothesis was in fact true and we chose to reject. These categories of mistakes are called errors, and there are 2 types of them. One of them is a type 1 error, the other one is a type 2, and normally the probability of a type 1 error is our value alpha that we've pre-selected, and the probability of a type 2 error is our value beta, which is determined from the particular test. So this column represents what's really happening, and these rows represent what we observe from our data. So we go ahead and we collect a sample, and we test the sample with a test, and we conclude that we do not reject the null hypothesis. 1 minus alpha percentile times, that conclusion will agree with what's actually correct. Beta times, that conclusion will be incorrect. We'll conclude that the null hypothesis is do not reject, when in fact we should have rejected it. We will conclude the alternative hypothesis is true 1 minus beta percentile times. And we will conclude the alternative hypothesis is true when in fact it's not, alpha times. And so that is the relationship of our alpha level, and beta is actually called the power, and our power level in these simple simple exclusive types of tests. There's quite a bit of other ways in hypothesis testing we're not going to discuss in this class. They'll get to you in statistics, because I just have to do the initial confusion. So each of these errors has a specific name. Type 1 error which is the incorrect rejection of a true null hypothesis, and type 2 error, which is the incorrect failure of rejection of a false null hypothesis or a false negative. And here's a picture cartoon to kind of explain these errors. And it's not meant to be offensive. It's meant to be somewhat humorous to give a very humorous perspective on these type 1 and type 2 errors. So in this upper left-hand picture, the doctor is consulting with the woman here who is clearly in the picture has a baby, and he concludes that you're pregnant. Now that's the case where the evidence supports the conclusion, and that is a true positive. That's this case here. So this doctor, not being the brightest, 1 minus alpha times will get it right. Occasionally, because the doctor's not too bright, he will talk to this elderly gentleman who, at least in our world, can't become pregnant by virtue of being a male and is unlikely to become pregnant by virtue of being almost as old as God. And the doctor says, you're pregnant. Now that's a false positive or a type 1 error. And that doctor is going to come up with that alpha percentile times. The true negative is the beta factor. So beta percentile, the doctor will conclude that the elderly gentleman is not pregnant. And 1 minus beta times, he will look at the clearly pregnant woman and go, you're not pregnant. And that is a picture to explain these categories here. So all statistical hypothesis tests have risks of making either of these types of errors. False findings are more than possible, they're probable. If we do enough experiments, we're gonna find false positives. Ideally, we want to pick a significance level that reduces the likelihood of one of these errors. For example, a very small significance levels, and of those significance levels such as 5% and 1% are common in many fields of science. Harder sciences, such as materials physics, dealing with carborundum and other hard materials, may choose more aggressive levels of significance. And you, as the experimenter, if you're actually doing the experiments and not just analyzing data, you can control the error rates of the true positive and the false negative, the false positive and false negative errors. You have control of that, but you can't drive either of them to zero, simply because there's not enough money, or if it's destructive testing, you're going to end up with everything broken. There's better explanations than what I've done. At these 3 references, statisticssolutions.com, abtasty.com, that's probably a pretty cool one, and then a Wikipedia entry. So some important statistical hypothesis tests that you're going to get exposed to today, a lot like ionizing radiation. There are tests that examine different distribution types. So there's a Shapiro-Wilks test, the Agostino's K-squared test, and Anderson-Darling test, and there's quite a few more. And what these are doing is testing whether a distribution based on sample data appears to be normal or not. And that's an important question to ask first, because if the evidence is that the data maybe came from a normal distribution, that allows us to use this parametric category of tests to ask the questions we really want, comparing sample means and analysis of variance. So these tests, students T, paired students T, ANOVA, repeated ANOVA, they depend on the underlying population distribution being approximately normal. If it's not normal, you can still certainly apply the test. The tests are just calculations. They're no big deal. They're just buttons on a calculator. But your attained significance values are going to be much worse than you think they are. So when the tests are not supported as Gaussian, our next tool in our toolkit is to go to a non-parametric series of tests. So the non-parametric tests, Mann, Whitney, Wilcox, Sign, Ranks, Kruskal-Wallis, Friedman, and there's quite a bit more. They don't particularly care what the underlying distribution is. They're all based on ranking things. And what you lose in those is the non-parametric tests have relatively low power. You lose control of your beta error. So these links are excellent links in these tests, and you can read about these on your own. You get to explore some of them in class. Let's just work through this. I've got a few minutes left. Let's work through a few examples. So the Shapiro-Wilks test is a tool that lets us speculate whether a data sample is normally distributed or not. And it assumes that each observation in the sample is independent and identically distributed. And our null hypothesis is that the sample is Gaussian distributed. Gaussian means normal distribution. Our alternative hypothesis is the sample does not have a Gaussian distribution. So that particular test is in Skippy Stats, and it's called Shapiro. And what it will do is it will return a computed statistic value, and it will return the associated p-value or attained significance of that data. So let's suppose we have this data right here, and I'm going to split my cell so that I can actually there's our data. 0.8, 2.8, 0.12, minus 0.9, minus 0.05, minus 1.4, 0.36, minus 1.4, minus 1.6. So we've got a lot of minus numbers and some small positive numbers. And if I recall how to do a histogram, oh, I don't have that easy. I don't have this in a pandas data frame. I was going to try to draw a histogram of this. We would see that there'd be quite a few bins between -2 and 0 filled with things. We'd have 1, 2, 3, 4 elements in the -2 to 0 bin, and in the 0 to 2 bin we have 1, 2, 3 elements, and in the 2 to 4 bin we'd have 1 element. So it would initial appearance be hard to tell if it's normally distributed or not. But if we apply the Shapiro data test and follow our guidelines that if the p-value is bigger than our alpha value, then we will conclude that it is probably Gaussian, otherwise probably not Gaussian. And we can get fancy. We actually can explore. So all I've done there is just made alpha an adjustable variable. We run that and it says it's probably Gaussian. Let's suppose that we want a more rigorous test. So this the evidence is that our distribution is pretty darn Gaussian. If we get weak on our alpha, okay, now that's making me scared. There we go. It actually did the switch point. But let me go back to the normal way of doing it. So we would conclude that 1, 2, 3, 4, 5, 6, 7, 8, these 9 items provide evidence that they are Gaussian distributed. And we would leverage that later on if we want to ask some questions about that. Another test for normality is called the Agostino's K-squared test. And it too tests whether a sample is Gaussian or not. Same underlying assumptions, each sample IID, and the same interpretation, the null hypothesis, samples Gaussian, alternative, samples not Gaussian. And it uses some different information from the test data. It actually computes the first 3 moments of the sample, 4 moments, because it's complaining about kurtosis. And this particular test is not designed for samples that are much smaller than 20. We have a sample size of 10, and so it issues a warning. Warning is a kurtosis test is only valid for sample sizes bigger than 20. It's continuing, it's going to report a result. But when you get a warning like that from a statistical test, that doesn't mean you quit. That means you read the warning. And so I would say, based on this test, while it reports probably Gaussian, because of the warning, I would conclude that it's probably only barely Gaussian. There's some more normality tests that are described by Jason Brownlee in a blog post called General Introduction to Normality Tests at machinelearningmastery.com. So let's now say we've decided that our data are indeed Gaussian. We now can apply our parametric statistical tests. So first, let's look at, there's our data from before. Let's go ahead and check this data here. See if it's Gaussian. Sure enough, our data 2 is also Gaussian. So now we're going to compare data 1 and data 2. While we're at it, let's go ahead and get the oh crap, this is not R. My bad. Sorry. I'm thinking in another language that has that stuff built in. And these are not pandemoniums. So we'll let the computer handle that for us. So we have data 1 minus 0.8, 2.8, and so on. And if we wanted to figure out what the, oh, it does have sum. We can do this. Sum of data. And I think there's 10 elements. So our mean value of our first data stream is minus 0.32. And our mean value of our second data stream is minus 0.15. So like with the money example, minus 0.32, minus 0.15, those are different numbers. So are these data streams from the same population or not? That's all the information I'm giving you. Are they from the same population or not? The two mean values. Let me put this up on the screen so you can remember it. Minus 0.32 and minus 0.15. Nobody's answering, so assume your short-term memory is performed as it usually does. Or more importantly, you don't want to take the risk on such little information. But we also could look at the variance. We could also attempt to plot it. Let's just use our student's t-test. And what the student's t-test is, it compares the means of two data series. It assumes that the observations in each sample or data series are normally distributed, and we've tested that conjecture already. And it assumes that the observations in each sample possess the same variance. And it tests the null hypothesis if the means of the sample are equal. The alternative is the means of the sample are not equal. So let's go ahead and test that. Probably the same. I'll just leave it. I'll leave it as is. So it's going to look at the two samples and return either that they came from the same population or they came from different populations. So we run it and it claims they came from the same population. And that's really weird because the mean values are different. More importantly, I want to look at the computed p-value. So this computed a p-value of 0.784. So that's an assessment of the difference in probability between the two series. Let's play a game. I'm going to repeat the analysis, except I'm going to make data 1 and data 2 identical. And with data 1 and data 2 being identical and in a data frame, we'll go ahead and repeat our calculations. So data 1 now has a mean value minus 0.32, data 2 mean value minus 0.32. Everything here is identical. So now let me go ahead and bring that up, disable that. And what I want to do is now test the probability that they're the same distribution. The answer should be yes, they are the same because they are identical data series, but I'm interested in what the p-value is going to do. I do that and it says a p-value of 1. So our test has the ability to determine, think of the p-value as a likelihood that the two data series came from the same distribution. So there's a 100% likelihood that data series 1 and 2 came from the same distribution because they're identical. When we go to one that has a slightly different mean, that likelihood of the sameness goes down. So there's a 75% likelihood that data series 1 and data series 2 came from the same distribution. And let's go ahead and wreck that. I'm going to hopefully shift everything the correct direction. Oops, that was my bad. I need to go more minus. So that should do the job. Now our likelihood that they're the same is quite low, 33%. And that's because of this one large negative value. So in your own work, don't be afraid if you forget how to interpret a particular test. Go ahead and test on identical copies of the data series to see what the reported p-value and statistical are, because that will help you tell how to interpret the results. And I often don't worry much about the alpha level in practice, but it's important in learning because it's all throughout the literature. Let me make this data to that guy. We can at least learn. I want to learn more about the two data series. So our data 1 had a mean value of minus 0.32, standard deviation 1.4. Our data 2 had a mean value of 0.15, a standard deviation of 0.83. So our data 2 series is actually quite a bit narrower than our data 1. Our data 2 might be the blue curve, and our data 1 might be the red curve. So another form of the t-test is where we're not sure that the variance in each sample is the same. And so instead, we're going to use paired samples. In a paired sample, there's a one-to-one correspondence. So if there are 10 data 1 items, there's exactly 10 data 2 items, and they're assumed to be paired. And so what it will do, it will compare them pairwise. And we're going to get the same result in this case. The analysis of variance tests, similar assumptions, but it's also testing the same interpretation, but it does it in a different fashion. It actually is behind the scenes performing what we're going to later learn is a linear regression and then interpreting the regression statistics for us. You can get more of this in your laboratory. And then the non-parametric tests, personal favorites because they're no brain required tests except to interpret them, no longer cares whether the samples are normal or not. It simply tests whether the distribution of two independent samples are the same or not. And it will do that by testing the mean value without regard to underlying distribution type. So gamma, normal, log Pearson, doesn't care. And in this case, these particular data series are selected so we're getting the same result. And then there is a sign rank test, which ranks the two data series and then determines the relative sign of them compared to one another. And in turn, determines whether they're the same distribution. The last one is Kruskal-Wallis. I'm just going to run it because I want to get to the example with real data. So I got 10 minutes to get through this example. And I believe you may see a restating of the example in the laboratory.
And
So here-
Dr. Cleveland, if you need more time, feel free to use it. The lab is not as heavy today.
All right. Well, this is it. I'm going to go through this example and
Awesome.
try to go slowly. So here's why you might use a hypothesis test. We're going to look at some data, and so here's one set of data. We have some dates, and we have total suspended solids in a stream, and we have the rain. 1, 2, 3, and we have the rainfall that occurred on those particular days. So look at total suspended solids. Well, actually, total solids, 400. Got a low number of 163. So some 600. So we're returning total solids in the range of 200 to 600 prior to construction, and then during construction, we have a lot more data, and our total solids ranges from 260 to 3,000. And the obvious question is, does construction activities in this regime have an impact on stormwater discharge? The intuitive answer is it probably does, but we can back that intuitive answer up with our observations. So by way of some background, Clean Water Act prohibits stormwater discharge. I'm going to read a lot of background simply to do a single statistics test. And rather than being mad at it, I hope I will communicate that that's a lot of how this is used in practice. Is we do a whole lot of problem statement development to run a single test to support a conclusion. Clean Water Act prohibits stormwater discharge from construction sites that disturb 5 or more acres unless authorized by an NPDES permit. Permittees provide a site description, sources of contaminants, appropriate measures to reduce pollutants. Appropriate measures are further divided in 4 classes: erosion control, stabilization, structural, stormwater management. Collectively, the whole thing is called a stormwater pollution prevention plan. And the permit itself contains no specific performance measures for construction activity, but states that, quote, the EPA anticipates stormwater management will be able to provide for the removal of at least 80% of the total suspended solids. The rules also note TSS can be used as an indicator parameter to characterize the control of other pollutants, including heavy metals, oxygen-demanding pollutants, and nutrients commonly found in stormwater discharges. Now, if you trust your EPA, what they've stated here is, we're going to demand that you use total suspended solids, which is a relatively easy measurement to make, and we're going to accept that it is also an indicator for other pollutants. So if you're controlling your solids, we assume you're controlling your other pollutants. As an environmental engineer, I could take them to task on that, but let's continue with the example. Because of that stipulation, solids control is critical to the success of a stormwater pollution prevention plan. And although the permits require the plans to be in place, it does not have any performance measures as to effectiveness. At least 20 years ago it didn't. And the reason was to reduce costs associated with monitoring. But unfortunately, the exclusion also makes it difficult for a permittee to assess effectiveness. And assessing the effectiveness will allow a permittee to defend themselves in court. So this is all because of lawyers. So if we hunt them down and get rid of them, we'll be fine. So here's our actual problem. We have two files, precon.csv and duracon.csv. You've seen the text file versions of those, contain observations of cumulative rainfall, total solids, and total suspended solids collected from a construction site on NASA Road 1 in Harris County, down by the Space Center. The data in the file precon was collected before construction. The data in the file duracon was collected during construction. The first column is the date that the observation was made. The second column is the total solids by standard methods, and the third column is total suspended solids by standard methods. The last column is the cumulative rainfall for that storm. Important note, the data are not time series. There's sufficient time between site visits that you can safely assume each storm is independent. Our task is to analyze the two data sets and decide if construction activity impacts stormwater quality in terms of solids measures. So there's a problem statement. Analyze the two data sets, decide if construction activities make a difference. So let me get some preloaded stuff in first. What does NumPy do? Seriously, people, you've been using it for the better part of a month. What's NumPy? I'm gonna go look on the chat. Maybe nobody wants to talk at me. A library for arrays. Thank you, Travis. What's pandas?
Ability
Data
to
frames.
read.
Pandas is a library for dealing with tabular data. Good. Matplotlib.
Imports, plots.
Cool. Okay, excellent. Very good. So you're all still here. I'm going to introduce something that I'm not sure we've shown before. I don't want to go to that web server and download files because I find that's a pain in the ass. It turns out that in our Jupyter notebooks, we can actually program that in and have it automatically get the files. The module we want to use is called requests. So I'm going to import requests, and then I'm going to set up an object called remote URL, and I give it the fully qualified name to the file. Now, arguably, how is that any easier than going to the website and right-clicking, downloading? For a one-of, it's not easier. But if I want to do this over and over again, as long as the webmaster of the remote website doesn't move crap around, I'll be able to get to that file for quite a time into the future, and I don't even have to remember file names anymore. So we set up the remote URL, and then I'm going to create an object called rget. I'm going to use the request module, and I'm going to get from the remote URL. I'm going to allow it to redirect so that it can follow any links on the remote server. And from the rget object, I'm going to grab the content and I'm going to write that to a file called precon.csv and store that locally. Then I'm going to do it again with the dircon.csv. So let me go ahead and download the files to my notebook. Done. So that was way easier than going to a remote directory, right-clicking, downloading, and getting it in the right place. Let's read the files. And I'm using pandas for the reader rabbit mode to read the two files. And so now I've read them. Let's take a look at the precon file. And there's the pre-construction file. Looks like it has 16 rows in it. And it has a total solids, total suspended solids, rainfall. And now I'll do the during construction. That looks like it has 36 rows in it and similarly labeled columns. So let's describe the pre-construction table. 17 elements, the mean value is 462, standard deviation is 361, lowest is 163, biggest is 1742, the median is 408. Let's look at the during construction. So we're using our friendly describe function, and let's see what we can observe simply from the 5-number description. Is the value of, let's do total sum. Let's do total suspended solids. Is the value of total suspended solids in the pre-construction phase? What can you say about that relative to the during construction phase? So as Farang does, somebody volunteer and interpret these two describe functions.
Well, it's obvious that in the TSS, there's a smaller mean compared to during construction. You can see that there's like a huge shift in the mean, the standard deviation, and the rest of our 5-number summary.
Okay, very good. So intuitively, we see from our 5-number summary that that during construction, there is an apparently substantial impact on total suspended solids or total solids. What about the rainfall? Because that's what's driving everything.
Could you repeat the question? Kind of cut out on me.
Pre-construction, during construction. What about the rainfall? Last column.
It was smaller.
In pre-construction, it does appear that all the numbers are smaller than the during construction, with the exception of the median and the 25th percentile. So in the during construction phase, we observe more slightly larger rainfall events than in the pre-construction phase. And that's not surprising given that we have nearly twice as many observations, twice as long in observation time. Let's go ahead and make box plots of the three things. Oh, good, it did it right. So here's our pre-construction box plot. And what did Farang tell you how to interpret these? If we look at pre-construction versus during construction, try to get them on the same screen. What do we see in the box plots immediately? Hopefully it's immediately obvious to y'all.
More dots.
Yeah, look at the up-down axis. The during construction up-down axis is at least 10 times larger in the same range as the pre-construction. So these numbers are all bigger just to start out with. We have these more dots. So assuming that we trust our computer program to identify what could potentially be high outliers, in the during construction phase, we have roughly 4 higher outliers, where in the pre-construction, roughly 1, and our rainfalls look about the same. So we see the scales of the two data sets are quite different. Let's see if the two construction phases represent the same rainfall conditions. So we describe the rainfall, pre-construction, during construction, and if we look at the summary statistics, we might conclude there's more rainfall during construction, which could bias our interpretation. So a plot of just rainfall itself might be useful. So if we do just the rainfall plots, we lose the axis difference in a big way. And it's hard to tell from the plots. They certainly look different, but are they? Well, let's apply some hypothesis tests, since that's the whole point of today. First, we'll do a non-parametric test, and we're going to test whether the pre-construction rainfall and during construction rainfall, whether there's evidence that they originated from the same underlying distribution, or there's evidence that they come from different distributions. So that's a Mann-Whitney U-test. Is the easiest to use in those situations. And notice in the Mann-Whitney U-test, we can supply our data series as actual columns that are taken out of a pandas table directly, and the Mann-Whitney code itself in Skippy stats is capable of determining that that is coming from a pandas table and converting it into the correct type that it needs to do the computations. And notice we've never even looked at the Mann-Whitney code. And this one concludes that these are probably the same distribution. Not super strong. It's roughly the probability of sameness is at about the 34% level, but certainly well above our alpha rejection value. There's not enough evidence that they're a lot different, so we conclude that they're not a lot different. We could also use a 2-sample t-test, assuming the data are normal. We've not tested for that. I can assure you from personal knowledge they're not particularly normal, but we'll just pretend they are anyway. And we get the same conclusion that they're probably the same distribution, but the p-value at rejection at this point is now completely absurd. Because they're not normal, there's no way that that p-value is at all reflective of what it really should be. And that's the risk of using a parametric test on data that are not suitable for parametric tests. You can still do the test. It doesn't care. Computer doesn't care. It's just doing calculations. But you, the analyst, have to provide the human input that as of today in artificial intelligence isn't going to replace that anytime soon. So from the two tests, the data are known to be not paired. We conclude that the two sets of data originate from the same distribution. Thus, the question, do the two construction phases represent approximately the same rainfall conditions, can be safely answered as affirmative. And notice what we did here. Perhaps you didn't see it because I didn't point it out. We've actually decomposed our overall test. We've applied decomposition. First, we're making sure the rain is the same. Because if the rain's not the same, it probably doesn't matter what the construction site's doing to the solids. So now we've convinced ourselves that the rain is same enough. And let me give, there we go. I got lost. It happens a lot. We've convinced ourselves the rain is same enough. So now we can test the actual treatment, whether the COVID-19 green pill is better than, blue pill is better than red pill. So now we're going to ask the same series of questions about total solids. First, we make the plots. Pre-construction total solids, during construction. Again, we get that huge axis magnitude shift. So the difference in scales suggests that there's something going on, but let's apply our test to formalize our interpretation. In this case, we're going to ask, do these come from the same underlying distribution or not? And we're going to choose our alpha value of 5%. We'll apply Mann-Whitney because I already know that these are not particularly normally distributed, and we get probably different distributions. So the Mann-Whitney test is actually looking at the sample statistic of mean value. It's also telling us that the mean values are different, and that difference has statistical significance at an alpha level of 5%. Our probability of variant rejection, or the probability of sameness, if you will, is 4%. There's a 4% chance that these samples came from the same distribution. Hence, there's a 96% chance they didn't. If we apply a parametric test, we're going to get the same conclusion, but again, the probability of rejection is going to be bogus. So these tests now indicate that the data came from distributions with different measures of central tendency. Now, for the hell of it, let's ask the question about normality. We're going to apply a test called normal test, and this function tests the null hypothesis that a sample comes from a normal distribution. The alternative, it doesn't. It's based on the D'Agostino-Pearson test, which combines skew and kurtosis to produce a total test of normality. And my notes say we're going to likely get a warning because our sample size is kind of small. So let's go ahead and see if the pre-construction total solids appears to be normally distributed. And it tells us it's not normally distributed. It also has warned us that our sample size is a bit on the small side, and it's designed for samples bigger than 20. So this warning, we wouldn't ignore it, but we'd be aware of it. That because of the small sample size, it can't effectively produce a p-value at rejection. But the results we're getting is that the data are probably not normal. And similarly for the during construction phase, we're not normal, but we didn't get the warning again. So what's different between pre-construction and during construction? Why did we only get the warning once?
We had a lot more samples during construction, like 40 something, I think.
Oh, correct. We had over twice as many samples. We exceeded this lower limit of 20, and so we don't get the warning in the second example. Okay, so I'm done. I've wasted most of your morning. Let's do a quick summary and conclusion as I hand this over to Farang. Hypothesis testing, its purpose in life is to help us decide if two data collections are similar or different. Helps us identify red umbrellas from black umbrellas. That's all its purpose is. It has some complex arithmetic behind it, and what we're really doing is we're applying calculation methods to give us a way of measuring distances between green and blue distributions, and if those distances are far enough apart, we conclude that our null hypothesis is rejected. If they're not far enough apart, we keep them. So that is all I have. Let me go ahead and not save that and return control to Mr. Farhang. I'm not putting words in his mouth, but he'll probably give you a 3-minute break.
So it is 11:42. We are going to begin the lab at 11:45. See you guys then. And I'm going to be here if you have any questions for me.
Good or not. I thought I was sharing my screen and just put a whole bunch of passwords up. It looks like I didn't.
No, no, you're good.
Okay. Oh, just to y'all, that's a really good chat transcript. That is really good. That's kind of how the chat transcripts are supposed to be. Cool.
I believe it stands for hexadecimal codes. That should be an easy Google though. Yeah, it's hexadecimal code.
You go ahead and when you do the notebook, just open a compute cell and show decimal to binary and then decimal to hex, and you can see what the hex function stands for.
Okay, Ferry.
Yes.
So in this case, what are we gonna put like over there at the X field? Oh, that's what you're working on right now?
You're asking about the hex code?
Yeah, like what should we put over there?
Yeah, I'm going to explain that in a moment.
Okay.
Go ahead and actually use the number 16.
16.
Yeah.
Okay.
When you convert it to hex, it should return 10. Yes, 0x10.
Mm-hmm.
And then if you do it in binary, do bin of A.
I'm not sure if it will print both of them. Yeah, I have to go with print.
Yeah, just wrap it and print. Let me see if I can do binary in my head while you're doing that. That would be 1, 8. It could be 1, 0, 0, 0 in binary.
So I believe this question is coming mostly from the first exam, and I think in that case we had asked you to give us the hex code based on your R number. So let's say that this is my R number. And if I feed this to the hex function, I'll get a code like this. That's what we were looking for. But if you didn't put it there, it's not a big deal, at least for the first exam. Do not worry about it.
Yeah, don't do binary. I just was, see, if you look at that number in binary, I mean, it's starting to look like Rambosian right there, which is a language from another planet.
Okay, do we have everyone here? Shall we begin? Okay. So I believe that when you went to the server to download the notebook for today's lab, you also downloaded 2 CSV files. Am I correct?
Yes.
Okay, I have a yes. Okay, great. One of those CSV files was the one that we used on our last session on Thursday. Is that right? I believe it actually reads lab 13 data or something like that.
Yes.
Okay, Cool. And the other CSV file has a more descriptive name, and it says student's performance. Am I right?
Yes.
Okay, awesome. So let us go on and begin the lab. This lab is titled Rejected or Fail, or a lab on hypothesis testing. Do you remember where we left things on Thursday? What did we do? What did we discuss? And where did we leave things? Caden, are you there?
Yeah.
So can you give me a brief review of what happened on Thursday?
1 second. We were looking at all the different data models and we were reading them in. We had the Weibull functions, histograms, basically just trying to like turn our data into plots, if I remember right.
Okay. James, are you there? James Phillips?
Yes, I am.
Do you have anything to add to what Caden remembered?
Over the last thing in the file.
Yeah, what we did in the lab on Thursday.
In the lab on Thursday, we went over the okay, it was like data distribution and like mean statistics. And I know for a fact that in the last portion of it, it was over like more so on the standard deviation and the graphs provided.
Okay, thank you. So as Caden and James explained, we worked on a data set with 2 sets of numbers. How many numbers did we have in each set? $100. Does that sound right? Okay. So then we use descriptive statistics to explore each set. We looked at the mean, we looked at the median, we looked at the range, IQR, all those good stuff. And we started to get some ideas about the spread and central position of each set. Then we used different plotting position formulas to get an empirical CDF for each set. When we compared the outcome of different plotting position formulas, what did we observe? Which plotting position formula was much better than the others? Do you remember this plot? So here we were comparing Weibull, Green-Gorton, Cunane, California, and Hazen. Which one of them was clearly better than the others? Are you guys on it together? Are you trying to hurt my feelings?
What was the question?
We looked at different plotting position formulas on Thursday. We looked at Weibull, Green-Gorton, Cunane, California, and Hazen. And we kind of compared them. So my question is, which one of them was clearly better than the others? And I have one answer from Travis in the chat box, and he says, wouldn't they all be the same in that graph? And the answer is yes, Travis. So we actually compared them and we realized that it doesn't make a huge difference to use either one of them for this specific set that we are dealing with. The answer is going to be very close. Then we looked at different histograms and we looked at KDEs, what did we infer from looking at the KDE?
Didn't we decide that there were bell curves?
Yes, we looked at it and we said, okay, they look kind of like a bell curve, and that gave us an idea on the underlying distribution, which was
Normal.
normal. Thank you. But we also looked at them and I asked the question, do you think these two sets are similar or different?
Different.
Different. That was the answer that I got from several of you on that day, and we also had a few of those who said they are the same. So if you want to simply look at this plot that I have on my screen and compare the range of the two sets, what can you tell me?
In the second set, we're gonna have a larger range compared to the that purple. Yeah, the purple set.
That is blue.
Oh my God.
Yeah, and I'm a man who is supposed to be colorblind. So come again, Caden?
That's unbelievable that she would think.
And they
Bro,
call us
looks
colorblind.
purple. It looks purple.
I think
No.
it's also purple.
Engineer. I think you need to think carefully about your future choices after that.
So it is actually navy. So it's bluer than blue. There is nothing purple about it. So what else can you tell me about these two sets by looking at this plot? For example, what can you tell me about the frequency of numbers in set 1 and set 2?
The frequency?
Like the height of these curves are indicating the frequency, correct?
Okay, well the navy one has a much higher frequency.
So because you're dealing with the same number of samples, when you reduce the range, those few numbers will have a higher frequency. But when you spread the range and you're dealing with a bigger spread, the frequency is kind of lower. Okay? So we then moved on and we fit a normal data model, and based on these plots, we said, they look like a good fit. And we decided to use that. Then we created a new sample set based on each set. How did we do that? Jalissa, are you there? I know you were there because you were just supporting Abby on her purple theory. So you are, but you don't remember. Okay. Nate, are you there? I don't remember either. Okay. Quentin, are you there?
Yes, I'm here.
Okay. Do you remember that we created new sample sets based on our original sets?
Not completely, but I do believe you. That makes sense.
Thank you very much for believing, man. Okay. So it seems that you were actually visited by this guy. Your memory seems to be completely erased. Do I have anyone in the room who remembers the fact that we did some resampling and we created set 1s and set 2s?
Wasn't it that we sorted them?
We sorted
No.
them to get the plotting position formulas right on top. Harper Hill saved the day.
Yeah, so we created a random number set using the mean and standard deviation of our sets that we had.
Thank you. One more question, and please do not fail.
Oh,
Why
boy.
did we do that?
Why? To create a new set that would be in a similar range to the set that we were basing it off of.
Thank you. So we had an original set. We took some steps and we realized, okay, a normal data model fits this set pretty well. We used the same data model to create a new set of samples. So we basically went from an original set of samples to a data model that can represent the population, and then we used that to get a new set of samples. Does that sound about right?
Yes.
Okay. Then we compared the 4 sets that we have right now. We have set 1, set 1s, set 2, set 2s. And we draw some box plots and some histograms. At the end of the day, I asked you 3 questions. Do you believe set 1 and set 2 are similar or different?
Similar.
I have 1 for similar.
Sorry, set 1 and set 2. Like
set 1 and set 1s, which are represented by 1 and 2 here.
yes, those are similar.
Okay, I have 3 more similars in the chat box. 4, 5.
They're similar.
Okay, do I have anyone who says that they're different? Jordan?
Yes, they are different.
Okay. But my next question will be for you. Would you say that set 1 and set 2 are more different or less different?
More different.
Okay. So at least we can deal on that. So we compared set 1 and set 2, and we say, okay, they kind of look different. That is very correct, Harper. And in fact, they are quite relatively defined. And that is exactly why we cannot simply look at something and go with a vague statement like that. So looking at set 1 and set 1s, we said they kind of look similar. Set 2 and set 2s, they kind of look similar, but definitely this couple are very different from this couple. That's where we left things last time. And then we said, how can we know if 2 sets are truly or significantly different or not? And then I said, this is going to be a special gift for Caden, who were really interested in the word significantly.
Well,
So,
dang, you can use the hypothesis test.
Exactly. So before I actually start talking about today's lab, can I get a confirmation on at least half of you that you do remember what we did on Thursday?
Yes, I do now.
Yes.
Okay. Okay.
Yeah.
You gotta kinda.
Yeah, and something quite scary from Harper that says remember is a strong word.
I couldn't.
So,
Do you have statistically significant evidence that you remember?
With a high enough sample size, perhaps.
so let us move to lab 14. On top, I'm actually doing a review of what we did. we are reading lab 13 underline data.csv. You already had this on Thursday, but we also give it to you again on the server for this lab. So you have multiple ways of downloading it. Then we defined set 1 and set 2. We created our sample sets, and we basically recreated the histogram and the box plot. So this is where we were. Now, based on what you learned today in Dr. Cleveland's lecture, we can use statistical hypothesis tests to confirm that our sets are from normal distribution data models. We can use the Shapiro-Wilk normality test. What is a normality test?
A test if our sample is representative of a normal distribution of a population.
Okay. And do you apply a normality test on one set, two sets, or multiple sets?
Multiple.
Two.
Give me the answers in the chat box. The ones that say single, the ones that say two, the ones that say multiple. Come on, start typing. Okay, single, multiple, multiple. Mult, because the IPL part is very hard to type. Multi.
We got a lot of smart Alex today.
I think you mean two. One is your data and the other is your guess. Okay, so Caden's answer is a little more descriptive, but keep on voting. Keep telling me what you think.
Can you repeat the question again?
Do you apply a normality test on one set of numbers, two sets of numbers, or multiple sets of numbers?
I said multiple. I don't know what happened, but you froze and it kicked me out.
Okay. So in fact, the only one that said single is Harper. And the rest of you said multiple. That is not the correct answer, but I really thank you for participating. And the rest of you, the good thing about Dr. Cleveland being in the room during lab is that when I am going to hurt you on the class participation, he will have enough evidence on that. Guys, wake up and play the game with me. This is a lab for you to participate and learn and make sure that you understand everything. Sitting there, playing with your phones, sleeping, eating, and not paying attention is not gonna have a good outcome for you. So we apply a normality test on a single set of numbers. We have a bunch of numbers, 100, 1010. That doesn't really matter. We look at those set of numbers and we say whether they are normal or not. We are not comparing two sets with a normality set or multiple groups. That's what comes later when we are talking about parametric tests, non-parametric tests. So a normality test like the Shapiro-Wilk test is going to be applied on a single set. Now, let's say that my set 1, which was one of the original sets that we had, I want to test that and see whether it is normally distributed or not. So from the SciPy stats, I'm importing the Shapiro function. This is what we need for doing a Shapiro-Wilk test. And I'm going to apply that on my set 1. And I'm going to say, if my P is greater than 0.05, I'm going to conclude that this is probably a normally distributed set, or probably Gaussian, or else not. So what is P?
Probability value.
Yes, or the p-value. What is the 0 point? Come again?
Isn't it 79.3%?
79.3%. Yes, that is the value that was calculated. Yes, thank you. What is the 0.05 that I'm using as a threshold?
Does that
Isn't it
mean? Oh
Alpha.
yeah, yeah.
oh, yeah.
Alpha, yes. Okay. What is this alpha?
It's a sentinel value to keep us honest to say if it's statistically significant or not.
Okay, so yeah, I actually like that definition. Is it always 0.05?
No, I don't even like
No.
No.
So
No,
if you want to be more confident about your conclusion, will you go with a higher alpha or a lower alpha?
Probably a higher alpha.
So if I say instead of 0.05, I want to go with 0.1, will you be more confident about your conclusion?
Yes.
yes.
I have a
Wait.
few answers in the chat box that say lower, 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 and then I wait. Okay, I'm waiting. I'm going to repeat the question again and give you a second chance. As a default and a very commonly used threshold, alpha equals to 0.05 is used to basically make a decision on the results of a test. In this case, we are saying if my p-value is greater than 0.05, I am not going to reject the null hypothesis, and I'm going to say that the set of numbers is normally distributed. But if my p-value is small enough, is smaller than 0.05, I'm going to reject the null hypothesis and say that the set is not normally distributed. Are we clear on that? Okay. Now, the question is, if I want to be more confident about the conclusion that I'm going to make, shall I go with a smaller alpha or with a larger alpha? Shall I go with 0.01 or shall I go with 0.5?
I would say 0.01 to be more
Okay,
accurate.
so you're still on the lower team, okay?
Lower.
Do I have anyone who says higher now? Jalissa, did you change your mind?
I'm still not sure because like if you increase it, or I think I'm mixing it up because if we have like an interval wider or narrow, I'm so confused. Hold up. Give me a second, please.
Okay. Your second is up.
Yeah, I feel like usually whenever you want a more, I don't know, I mean, because I feel like usually whenever you're doing experiments, you want a larger, like, I don't know, range. That's not the right word. You know what I mean? Like this is
I think I do what you mean. I know what you mean.
Yeah,
So,
that's what I'm thinking too.
so I don't understand how a smaller.
I want you to remember that there is a difference between significance level and confidence level.
Maybe smaller is like oh, I forgot what I was gonna say, is more accurate to, I guess, measure than a larger one, more specific.
So, as I have been warning Caden for the past week, be careful with the words because right now these words are having a quite heavy definition in the statistics. So, when you say accurate, I have to say no. But when you say that I can make a stronger conclusion, or I can be more confident in my conclusion, that is something that I can agree with. So here is the answer. When you go with a lower alpha, you will have higher confidence. So if instead of 0.05, I go to 0.01, I am actually increasing my confidence level.
Okay.
Do I have any questions on this?
No, I was just overthinking it too much.
Repeat it one more time. I had a phone call, sorry.
Okay, so before I repeat it, let me tell you something about the entire hypothesis testing p-value thing. It is ridiculously easy, and it can be ridiculously confusing. So make sure that every step of the way you are following and you are understanding the easy concepts, because it is very easy to lose track of them. So we're running a test. That test is going to give us a p-value. Based on the comparison of that calculated p-value and the threshold known as alpha or significance level, we are going to make a decision to either reject the null hypothesis or fail to reject the null hypothesis. Are we all good on this? Okay.
Yes.
Basically, what we just said is, if I increase the alpha or the significance level, I'm going to reduce my confidence level. So if I go from 0.05 to 0.55, I have reduced my confidence in the conclusion that I'm going to make. If I reduce alpha, if I go from 0.05 to 0.01, I have increased my confidence. So lower significance level, higher confidence. Higher significance level, lower confidence. Do we all agree? So I have, wow, today is extremely weird. I only have 36 students in the room. Yeah, I think for some reason people don't like me anymore. I don't know which one. So,
nice day outside. That's why they're blank.
So 30, 36, 35 students that I have in the room. Can I be sure that you understand how the p-value and alpha are working together?
Yeah.
Yes, sir.
Awesome. Okay. Now, we run this on our set one. We get a p-value of 0.793. Is this a high value or is this a low value?
A pretty high value compared to 0.04.
Yeah.
Exactly.
It's high, but not as high.
As
I don't know. It's a high value, but it's like it could have done better. I don't know, like
regardless of the problem that we are dealing with, a p-value can have numbers from 0 to 1 because it is a probability, correct? So if you look at that range, falling at 0.793 is on the very high end. Okay, so we compare this 0.793 with our significance level, which was 0.05, and we are going to conclude that set 1 is probably normally distributed. Question: why, even though I have run the test and I calculated p-value and I compared it to my significance level, I'm still saying probably?
Because it might be a bad sample.
Because you're not quite sure.
We're just
Why?
inferring.
Why am I not sure?
With an alpha value of 5%, 1 in 20 times you do this is going to give a false result.
Come again?
Well, your alpha value is 0.05. It gives you a 0.05. That gives you a 5% chance that it's going to fall under that, even though it is normally distributed. It's 5%.
Okay.
You're going to get a false.
Can you think of other reasons as well?
Could it be a bad sample or a small sample?
Exactly. There could be some issues with our sample. And in a very simplistic way to answer the question, this is life. You simply cannot be absolutely sure about anything. So dealing with the statistics, that is one of the things that you will learn and you can use on a daily basis. There is nothing that you can be absolutely sure about.
At the taxes.
So ask Jeff Bezos about that. Let us move on. We are going to run the same test on our set 2. We are getting a p-value of 0.151. Comparing that to 0.05, it is still higher. And we are going to say that this is also probably normally distributed. Question: if you compare the results of this test on set 1 and the results of this test on set 2, what can you tell me?
Can we say that the second option will be better in the sense that the p-value is lower for the second one?
So when you say better, you are still adding a little subjectivity to it. Better
Probably.
for who?
For the choice.
I didn't hear that, Anta. Can you repeat that?
Sure, like for the choice we want to make, if I can say it like that.
Okay, let me give you an example and we will come back to this.
Okay.
I'm going to ask you to sit behind a desk.
Mm-hmm.
And people are going to walk into your room.
Mm-hmm.
If they have a blue bag, I
Mm-hmm.
want you to give them a chocolate.
Mm-hmm.
If they have a red bag, I want you to shoot them.
Mm-hmm.
Okay?
Mm-hmm.
Clear?
Mm-hmm.
The first guy walks in, blue bag. What do you do?
Give him a chocolate.
Okay. The second guy walks in, red bag. What do you do?
I'm going to shoot him.
Wow, you're brutal. Okay. The
That's
third
what
guy,
you told me.
the third guy walks in and he has an orange bag. What do you do?
Do anything because
You only have two options. Do you feel better about shooting him, or do you feel better about giving him a chocolate?
because orange is closer to red, I think that I'm going to shoot him.
Okay, very good call. The next guy walks in. Actually, this one is a lady, and she has a purple bag, and she claims that it is purple.
Mm-hmm.
Would you
I'm
go
going to
with
give
chocolate or? Okay, so you dealt with 4 people.
Mm-hmm.
Do you feel more confident about your decision on the first 2 or on the second 2?
On the first 2.
Why?
Because, okay, I know what should I do if I have, if I'm dealing with somebody with a blue bag and somebody that has a red bag, while the other 2 one of them has an orange one and the other one a purple one. So I don't really know what to do. Yeah.
So to make a connection between that example and what we have here,
Mm-hmm.
the further you are
Mm-hmm.
from the threshold of decision making, in this case 0.05, the more confident you are in making a decision.
Could you repeat that, please?
So
Mm-hmm.
if my threshold is 0.05
Mm-hmm.
and I get a p-value of 0.1
Mm-hmm.
and I get a p-value of 0.7, in
Mhm.
which case am I further from the threshold?
The first one?
The first one, because this is 0.7, this is 0.1, this is a way bigger number.
Yeah.
The further I am from the threshold, the
Mhm.
more confident I can be in making a call.
Oh, okay, I got it now.
Okay, so
Okay.
in this case, it is like the guy with the orange bag.
Mhm.
In this case, it is like the guy with a red bag.
Okay.
You're more confident in shooting this one.
Okay, thank you.
Yeah. So that was actually the point that I wanted to make. So judging the results of a test by comparing the p-values is something that can be quite insightful. So if you wanted to look at these results and tell me which one of these sets has a closer nature to a normally distributed set, which one would you pick?
The first.
The first.
Why?
Larger value.
Exactly, larger p-value. Okay. Are we all good about this?
Yes.
Are we clear? Okay,
Yep.
awesome, awesome. So when Dr. Cleveland was teaching you about hypothesis testing a few minutes ago, he talked about basically 3 different categories of tests. One of them was normality test. What were the other 2?
Was it student? One of them?
That was a test, but that falls under a bigger umbrella, which is oh my God.
We we have parametric and non-parametric.
Okay, yes, thank you. So normality tests, we looked at them, we talked about them. Then we have parametric tests and we have non-parametric tests. Very important question. What is the difference between parametric tests and non-parametric tests?
The parametric part?
Oh, really? So have you heard this term before in your other courses, parametric, non-parametric?
In a math class.
Okay, can you remember what was that about?
It's when we take something and like we change the variable so it'd be like t.
Okay.
We parametric. We make it was like a class of equations, like parametric equations, where we would write it like x equaled t something and then y equaled t.
Okay. So I think that is probably causing you to overthink this. The difference is very, very simple. If you assume that your sets belong to a normally distributed format, you use parametric tests. If you do not, you use non-parametric tests. In other words, parametric tests run based on this assumption that your set is normally distributed. If for any reason you cannot meet that requirement, if you do not have that item checked, you cannot use parametric tests and you should use non-parametric tests. Are we clear on that?
Yes.
Okay,
Yes.
awesome. My next question is so important that you're going to see that as an exercise sometime later. Why do we care about normality tests? Who cares if your set is normally distributed? I literally just gave you the answer less than a minute ago.
To see what hypothesis test we're gonna run.
Exactly. You run a normality test to see whether you do meet the normality requirement for parametric tests or not. If you run a normality test and you decide that, okay, my set is normally distributed, you can go on and use a parametric test. If you run a normality test and your set is not normally distributed, you cannot use a parametric test. You have to use non-parametric tests. Are we clear? Okay, awesome. So we are going to confirm that set 1 and set 1s are from the same distribution. We are going to use the Mann-Whitney U-test for this. Mann-Whitney U-test, is it parametric or is it non-parametric?
Non-parametric.
Non-parametric. Didn't I just say that my set 1 is normally distributed? How can I use non-parametric tests on a normally distributed data?
I guess it would be changing your hypothesis statement.
The thing is, regardless of whether you are normally distributed or not, you can always use non-parametric tests because they are not the one with an additional assumption requirement. For parametric tests, you have to check and see whether you are normally distributed or not. So on a case like the example that we have here for our set 1, which we just decided that it is normally distributed, we can use parametric and non-parametric tests depending on what we want to do. Okay, so a Mann-Whitney U-test. What are we looking for? What is the question that we are trying to answer with this test?
Trying to look if they're the same distribution.
Okay, good. So we are comparing and we want to see whether they belong to the same distribution or not. Do we run this test on a single set of numbers, 2 sets of numbers, or multiple sets of numbers?
2
numbers.
I have 2 2s in the chat box. Caden also said 2. 2, okay. Double voting there. 2, 2. Yes, that is the correct answer, though. We run this test on 2 sets of numbers, and we're going to compare those sets. So here, I'm importing the Mann-Whitney U function from the package, and we are applying that on set 1 and set 2, and we are going to compare the p-value with 0.05 again and decide whether they belong to the same distribution or not. The null hypothesis of Mann-Whitney U-test is that the 2 sets belong to the same distribution. So if your calculated p-value is small enough that falls below your significance level, in that case, you will be able to reject the null and say that they are not from the same distribution. They are from different distributions. If your p-value is not small enough and it is larger than your significance level, you are going to conclude that they probably belong to the same distribution. Do you notice the similarities and differences between this test and the normality test that we just worked on? In both cases, we are using the calculated p-value and comparing it with the significance level to make a call. But the kind of call that we are making is different because we are using different tests. In the first one, we were between normally distributed, not normally distributed. In this one, we are between coming from the same distribution, not coming from the same distribution. Are we all good?
Yes.
Are you on top of this?
Yep.
No.
Okay. That was an honest answer. Do you need any help? Do you have any questions for me?
No, I'm just gonna have to sit and think about this for a while.
Yeah, I agree. I agree. Okay. We ran the test. We got a p-value of 0.4, which is way bigger than 0.05. So we're going to conclude that set 1 and set 1s are probably from the same distribution. Running the same thing on set 2 and set 2s, we get a p-value of 0.3, which again is larger than 0.05. So we're going to conclude that these two are also from the same distribution. Did we know this already?
No.
Yes, because we ran the other two.
Yes, because we actually sat on God's chair and we created set 1s and set 2s. So that, for a moment there, that's how God feels. He knows the stuff, but he allows you to run your tests and confirm them. He already knew. So let us move on and compare our set 1 and set 2, the ones that we initially begin with. Do you remember looking at those histograms and those box plots and everything, and we kind of realized that they look quite different? Now,
Yes.
we are going to run the same test on set 1 and set 2, and look at this p-value. This is awesome.
Very high confidence level.
Yes. So you are quite confident that set 1 and set 2 are coming from different distributions. And now this is more than simply, I feel they're different, but they're not, and something like that. So this is where someone like Jordan can come in and say, even though set 1 and set 1s looked a little different, but their difference is not significant. Here is where someone like Caden can come in and say, I think set 2 is significantly different from set 1. The word significantly comes from you comparing the p-value of the test that you're running with your significance level.
Can you get any more confident than 0?
P-value is a probability, and like any other probability, it can only go from 0 to 1. So in fact, probably if you had more numbers on this side, it would have been 0, 0, 0, 0, 0, 0, 0, 0, 1. But for all realistic purposes, you can play with this up to probably this. Dr. Cleveland is here, so he can give us a better idea. I've never seen a p-value smaller than this in a real practice. Dr. Cleveland, have you seen anything lower than this?
What, smaller than 0?
I mean, significance threshold smaller than 0.001.
That'd be 0.1%. That would be unusually small.
Yeah.
Almost to be meaningless.
Exactly.
is when we get in interval estimates next week, you'll see the impact of alpha on such estimates.
Okay, so I have one more example for you. This is based on a real data set to give you a better sense. So a data set containing marks obtained by students on basic skills like math, language skills, reading, writing is collected from an educational institution, and we have been tasked to give them some important inferences. So the hypothesis is that there is no difference in means of a student performance in any of basic literacy skills, reading, writing, math. And by the way, this example is based on what you can find on this blog post. And the data set that we're using is also freely available on Kaggle. So the student's performance CSV that we've given you, oops. Looks like this. So these are the information that we have on our students, and these are their grades. So the hypothesis is that there is no difference between this set of numbers, this set of numbers, and this set of numbers. So before looking at what I've done and what I have and what you have in your notebooks, can you tell me an algorithm for how we should proceed? What should we do?
What are we trying to do?
Exactly, that's my question.
Well,
So
I would
the hypothesis that one moment. The hypothesis that we're given is that there is no difference in means of student performances in any of these grades or scores, and we should kind of provide a statistically significant evidence. Go on.
I would make a distribution of the mean of the math score separate from the reading score, separate from the writing score, and then compare those.
Okay, so you want to create 3 sets of numbers and then see whether they are from the same distribution or not.
Yeah, it ignores a lot of our data though.
Do you know how many entries we have in this set?
1,000.
It's not bad coming from the school.
Is it 5?
When you run the head function, it gives you 5, but when you look at the beautiful describe function, it tells you that we have 1,000 records. So looking at the results here on this summary table, what can you tell me about the mean and median of these scores? Do they look similar? Do they look different?
Well, looking at 66, 69, and 68, not knowing that there was 1,000 entries, I'd say, yeah, those are probably pretty similar.
Okay. What can you tell me about the median?
Also pretty similar, and pretty similar to the mean, so it doesn't really, not sure it matters if we use which here.
Okay. But looking at the minimum number, that gives us a little bit of a difference, right? The minimum grade that we had in reading was 17. The minimum reading that we had on writing was 10. And we had someone who got a 0 on math. So yeah, that can happen. So comparing IQRs, what does that tell you?
They're pretty acceptable size. It's pretty small.
So looking at this table, if you want to tell me whether you think the scores in math, reading, and writing are close or far, what can you tell me simply based on this table?
My intuition tells me that math and reading are going to prove different, but reading and writing are going to prove close.
Okay. I have one answer from Caden, one from Nate. The rest of you, wake up, wake up.
Close.
Close.
They're going to be close.
Okay. Okay. So moving on, I'm going to define 3 sets. Set 1 is going to be my math scores. set 2 is going to be my reading scores, and set 3 is going to be my writing scores. And I'm going to import the Seaborn external package, and I'm plotting the histograms with a KDE using the dist plot. We have already discussed this. And I want my x-axis to go from 0 to 100. Why?
Because test scores are on a range value from 0 to 100.
That is the possible scores that I can get, and I set the label. So looking at this, we know that my set 3 is green, my set 2 is dark orange, and my set 1 is blue and not purple. Do you think they are coming from the same distribution? Do you see any difference that you believe can be significant?
I stand by my original. I think the Navy is going to prove a different distribution, and the reading and writing are going to prove the same.
Okay.
They look similar, but they are different.
You could see that there's a small difference in how they're skewed, so maybe there could be a small difference, maybe.
Okay.
Oh,
So
I'm sorry.
no, go
I
ahead.
would say that the median is different, because if you look at the blue one, it seems that it's by 60, and the other one is probably by 80 or 70, something like that.
Okay, so you do see a difference between the peaks. Yeah,
Yeah.
that is good observation. So I actually liked many of your answers, Caden, Abby. It was all good. So we are going to set up our null and alternative hypothesis and then run some tests. So do you agree with this combination? My null is going to be there is no difference in performance of the students between math, reading, and writing skills. My alternative is going to be there is a difference in performance of the students between math, reading, and writing skills. Does this sound fair?
That's fair.
Okay.
Sounds good.
Do you know how I came up with my null hypothesis?
It came from what the question is asking for.
Exactly. It came with the problem statement, and that is something that can happen to you in a real life situation. They come to you, and you can base your null hypothesis on their assumption or on something that they suspect might be true, if you have no idea. So I'm going to use the Mann Whitney U test. Why?
Well, because we haven't actually tested if it's normal, even though it looks like it, and it works if it is or if it isn't, so whatever.
Exactly. So since we have no idea whether they're normally distributed or not, we are going to use a non-parametric test. And we are testing set 1 and set 2. What are we testing?
Set 2.
Math and reading. And we get a very small p-value, which means
different.
They are from different distributions. We are going to compare set 1 and set 3. And we are getting, again, a small p-value. It's not as small as the other one, but we are looking at 0.001, which is less than 0.05. So it means that you have enough evidence to reject the null and say that they are from different distributions. So 1 and 2 were different, 1 and 3 were different. Looking at set 2 and set 3, we get a p-value of 0.067, which is larger than 0.05, so we cannot reject the null. But I want you to pay attention to how different this number is from your threshold. So it's not that big of a distance. So anyway, based on this test, on this significance level, you're going to say that they are probably from the same distribution. Now, I have a question. Is there any way that we can compare 3 sets of numbers at the same time?
Yeah, probably.
Is it student test or is there another test?
Student test is a parametric test, but in the realm of non-parametric tests, we also have an option that allows us to compare multiple groups. And here I have an example of that. That is the Kruskal-Wallis test. This beautiful test is going to allow us to compare set 1, set 2, and set 3 at the same time, and with a significance level of 0.05. We are going to basically say if my p-value is greater than this, all three are probably from the same distribution, and if it's not, at least one of them is from a different distribution. And running this gives us a very small p-value, which means that between set 1, set 2, and set 3, there is at least one of them that is different. Fair?
Mm-hmm.
So as an exercise, I've given you this. Isn't the Kruskal-Wallis test missing something? In the last example, we used the Kruskal-Wallis to check whether the three sets belong to the same distribution or at least one of them is different. The question is, how can we find the sets that are different? What is the missing piece in tests such as the Kruskal-Wallis test? So that is for you to go and find. I have given you some interesting references on hypothesis testing, data science, and Python. I definitely recommend having a look at them, and then some videos. I honestly think these four are way better than the videos on this specific topic.
Farhan,
Yeah.
I'm not sure I understand the question. Are the missing piece, are you saying that you misapplied the Kruskal-Wallis function and there was something else that you should have put inside your code block to tell us something else?
No, Caden. So I run the Kruskal-Wallis and it told me that my p-value is very small, smaller than my significance level, and it said that in the three sets that I compared, there is at least one of them that is different from the others. Fair enough?
Yeah.
But is this enough information for you? Don't you want to know which one or which ones are different? That is what I mean by the missing piece. So yes, you said I'm comparing three and I now realize that at least one of them is different. But which one is that one? Is it only one of them that is different, or all of them are different from each other?
So are we so we're saying either if one is different, we state that one that is different, or I don't really understand the question.
So my question is not case specific. If you look out there, there is another follow-up step that you can take after running a test like Kruskal-Wallis. And in that follow-up step, you will be able to say, okay, these are the ones that are different from the others. And if I have anyone in the room who wants to give us the name of that follow-up step, they are more than welcome to. Have you ever heard of a post hoc test? It's all right. You will learn about it.
We'll learn about that.
Yeah, do some Google, and you will know about it. I don't want an entire lecture on it. It's very similar to your previous exercises. A paragraph would just do, but do your lookups, use your resources, and come up with a good answer. Do I have any other questions? Okay, and that was what I had for the lab today. Thank you very much for paying attention, the ones that were more active. Thank you. I am going to pass the host back to the boss.
All right, well, that was your introduction to hypothesis testing. On my video screen, what you see me is not my pretty face. You see a drawing that is an attempt to completely obfuscate everything we've just done for the last 3 hours. So let me go through that drawing. It'll take a minute, and then you will be free to go. Imagine, if you will, that we have collected 2 samples, the one on the left, the one on the right, and we fitted a population distribution to our red samples and to our blue ones. And if we were to plot those 2 on the same random variable axis, that's what the plot looks like. So not a whole lot of overlap. Red and blue are clearly not much overlap. Now let's change the game slightly. Same story, but now they plot where there's considerable overlap. All of our hypothesis tests are premised on an conjecture that we can determine the overlap between our red and blue. All we have is the samples to work with, so we are implicitly fitting a red and blue curve. And that p-value is essentially the area under the overlap. If they perfectly overlap, what should the p-value be?
1.
1. And if they're this case, what's the area that's of overlap? Essentially
Usually 0.
And in practice, we're working between those 2 extremes. The alpha value is something that we a priori stipulate on when the area is too big or not for our uses. And that's all I wanted to do to obfuscate things. It's a damn shame that we can't generate this plot on the fly really easily. But I can draw it faster than I can program it. So
even in stats, even in statistics, I hadn't seen that visualization. I really like it.
That's because I'm not a statistician. So I had to come up with something that explained it to me. And notice
that's what you get when you take your classes with the cool engineers.
So
yeah, I assure you that probably we're the only sections that are showing this picture. I'm going to take it away, and I'm going to wish you all a wonderful afternoon. I'm looking out my window. It looks beautiful outside. So if you have an opportunity to get outdoors for a few minutes, by all means, enjoy it. And we will see you on Thursday in the class. And I have office hours tomorrow. I think I'm 4 to 5.
Yes, sir.
And Farhang is 5 to 6.
Yes.
So remember, you have a lot of things due this week, so stay on top of that in this class. Get the easy stuff done as fast as you can and submit it so it's off your book to free up time for the hard stuff. Everything has multiple submissions, so if you want to partial submit some of the harder stuff, so that if you run out of time, you at least get some credit for it, that's a good strategy too. And with that, have a good afternoon. Bye-bye, everyone. Oh, wait,
Take care. Be safe.
I'm waving at a camera that's not looking at me. There we go.